we're out, it's a wiki-style tree, out to have everyone put in their genealogy, share that, since we all share a common genealogy, and ultimately our goal is to have one pedigree of all the human family that is on record here on Earth. Let's see. So I would be amiss if I didn't make just a short plug for why we do that. The Mormons have a doctrine that's a little bit different from many churches, and we believe that all of mankind, even those who did not have the opportunity to hear about Jesus Christ, can be saved. And I'll say one more on that. If you have ever been up in the middle of the night and wondered what the purpose of life is, why we're here, is there really a God? Does he know me? And does he care? I assure you that the answer to all those is yes, and that there are logical, rational, and answers to those questions that bring peace. If you want more on that, mormon.org, or come see me afterwards. Okay, so the family tree application. Currently, it's just over 900 million persons in there with about 500 million relationships. We record things by changes, and I'll talk about the data model here in just a moment. 8.4 billion changelog entries, about 1 million changes a day come in to those, and all that equates to currently about 7 terabytes in Cassandra, 13 terabytes in Oracle. Our current system is on Oracle, and we have a intimate and painful relationship with Oracle for quite a while here. So when you're in a pinch and you need to scale Oracle, it is possible to fork over lots and lots of money for hardware and scale up Oracle, and that's what we have done for a number of years. And so my group is a research project to get off of Oracle onto Cassandra. So we went through a progression here. We first went on Mongo and did a bunch of testing with Mongo. Decided we needed to do a side-by-side with Cassandra. We did that and went with Cassandra. 2 main reasons: better performance, and administratively it was better, it was more stable. So we are an online, an OLTP system, online transaction processing. Users expect their changes to show up right away, at least for them. And so there's that transactional side that we have to maintain. And we have some interesting data-related performance issues. You might think you could assume that people usually don't have more than, say, 20 children. However, everybody here probably has stories about crazy data that you encountered. Well, we have people with thousands of children. And yeah, there's interesting histories on how that happens. But there you go. Similarly, people have one set of biological parents. But again, through oddities and how people use the system, we come up with dozens of parents. And so we have these issues that have been painful to resolve because people still want it to render and at least show them that that's what's going on, right? So a couple of screenshots. This is what we call a fan chart. You see there's me down there in the middle. That's the circle. I have 2 parents. That's the next ring. They each have 2, and this goes back 9 generations. There's 511 slots on there, and we want it to render like that, right? Everybody's used to that. And so you have to walk those relationships to generate that thing. This is actually done through a partner that we provide APIs for everything we do. So we have many partners that offer things based on our data. Here's another screenshot. This is now the interactive pedigree. The other one kind of gives you the forest. Now you drop down to the trees. And there are 2 red rectangles here. The one on the left is kind of the default view when you come on, and then you can expand. We currently have big performance issues trying to render this. So in just pulling enough records out of Oracle and walking them to render it. And so that's what we are out to fix and scale at the same time. Here's a shot of the person page. Again, those families can be an issue. It's not uncommon to have to load dozens of people just to show the spouses, children, and parents and siblings of a person. on there. And then we've had some real issues with the change history also there. There can be thousands of entries that we need to go through to render that change history. Okay, the data model we use at a, this is our new data model. It's event sourced. That means there's two data models actually, one for writing and one for reading. The journal, I've pictured here on the left, is a series of journal entries, and we always write to that. So an example of a journal entry would be, change the name of this person from Mike Nelson to Michael Nelson. A change like that. Or add this relationship to a person. Any kind of changes always get written to journal entries. They are immutable. They never change. So if you want to fix the record, you always append another journal entry on. That does a couple things. We're using time-based UUIDs as the key on those. And that means you can be inserting from to the journal, multiple application servers can be inserting at the same time, and they will always resolve to a coherent view. So there's no locking at all necessary. So that's the writing. When you go to read, that always comes out of what we call views. And there's two of them shown here. For person 1, I show 2 views, A and B. We actually have 3 views currently that we compute. So one's a full person view. Here's the current snapshot of the person, all the information about them, and everyone they're related to. There's a summary view that's just basic information, name, birth, death, and places for those things. And again, who they're related to, and there's a change history view that we do there. So what that does is all the business logic goes into when we write, and then when we compute the views, and when there's a read, Cassandra has exactly what we need. And it's a simple lookup and return it in every case. So we get the benefits of the denormalization. There, the view has exactly what we need. Okay, so we're talking performance, so you need to know some basic information about us here. 77% of our traffic are reads, 23% writes. So that's pretty typical, being very read-heavy. Our reads are consistent. Almost always consistency level 1. There are a few cases we're not. And are very simple. Writes are much more complicated. We're using atomic batches and quorum consistency level for the writes. The writes also go to multiple tables. This is the reason for those batches. So if you write a journal entry, we're writing it into the journal itself, column family, but then also to each of those views so that then the view can be incrementally updated from there. So it's not uncommon for some operations to involve a dozen rows. So for example, if you're adding a parent on a person, it's going to affect multiple people and multiple relationships and views for all of them. So there's a number of tables there. And then business logic. There's some pretty basic things that we have to enforce, and they can be quite complicated to actually enforce. So for example, we will not allow you to enter a relationship that will make you your own grandfather or grandparent. Right? That's obviously incorrect. We won't allow that. Okay, so we've done a series of tests earlier this year on a 28-node cluster. Learned a lot of things, did a lot of optimizations on the application, and I'm just going to talk here about the optimizations that were Cassandra-related optimizations. So overall, we ended up with about a 10x improvement in what we could scale to, but you're not going to be, maybe you'd be interested, but I'm not going to share the the application-specific optimizations. So the tests earlier this year were on a big cluster, 28 nodes on Amazon. That is, all of them were high 1.4XL nodes, so that's 450 cores in that cluster, and we got to 250,000 ops per second. I went back and did a series of tests in preparation for this presentation on an 8-node cluster, and with all the optimizations that I'm going to show you here, at least those were most of them were not the application. I was able to get up to 200,000 with just the 8 nodes. So it makes a little optimization goes a long ways here, and those are very expensive. The high 1.4XLs are very expensive. There's a lot of cost savings there. Okay, so the test system that I used here, an 8-node cluster. As I mentioned, high 1.4XLs. Those have 16 CPUs each, 60 gigs of RAM, and they are SSDs. And then I put the app servers up here. Purposely did more app servers and more load runners than load agents than were required, because the purpose was not to test the app here. I was trying to push Cassandra. So I wanted to make sure there was plenty of CPU and network for the app. And I should mention here, it's using Borland Silk Performer for the load, to do the load on it. We did some stuff with JMeter. We had some issues. We went to Borland Silk Performer. We've had some issues, and we're talking about going back to JMeter. So it's yeah, that's been fun. Okay, so here is the summary. What I found overall. The two big gains for us were in the row cache and making the driver token aware. And overall, Cassandra's been pretty stable for us. We've had a few incidents. We have our first Cassandra cluster in production right now. That is not Family Tree, not this app. It's a different one. And no big incidents yet. Overall, I've been pretty impressed with the stability. We're using SSDs for everything here. So the big advantage that we've found with SSDs is that repairs become a non-event. So I hear all these people with lots of pain around repairs, and we just haven't had those. So for example, if I can do a full repair on all the nodes simultaneously on the 8-node cluster, and it takes about 4 hours, and load never hit more than about 2 on any of them. And it doesn't saturate the SSDs. So lots of headroom there with the SSDs. So overall, it was about a 2x throughput increase. Okay, so row cache. Yeah? I'm sorry?
What's the load size?
It's about 7 terabytes on here, and replication factor 3. So it's about 900 gig on each node. Does that answer the question? Replication factor 3. Yes, yes. So row cache. We have a good-sized data set, 900 million persons, but there's a lot of, the working set is not nearly that size. And so on an 8-node cluster, we can fit the working set in RAM. And that's why I believe the row cache was a big benefit for us. We put the views, they're small in the row cache, not the journals themselves. And the reads are consistency level 1. So that means that all that can be in the row cache, and we get hits and a nice bump from row cache. Latency went from 11 milliseconds down to about 7, and a 35% bump in how much the cluster could handle. And I should mention I was pushing the cluster as hard as I could in every case here. Took the load agents and said, push it just as hard as you possibly can. And so all the nodes go yellow, and Op Center thinks we're sick, but get as much out of it as we can. Average row size, and what was the other question? How many columns? So in the views, there's typically only 5, I think 5 columns. The journals are different. There's a column for every journal entry, so there can be thousands there in those. What was your first question? Row size. Row size. So the views, it depends on the column family. What's average? Where's John? It's, let's see, we're probably between, 1,000 bytes up to 50K is typical, which is fairly small. That's why row cache worked well for us there. They can get big. They can get up to half a meg, but it's not typical.
Does this depend on the depth of the family tree? Like, does this one dictate the row size in your application?
No, it's the individual view of that person. So if they have the person that has 1,000 children, will have a big view, but most don't. Most are not that large. Okay, so the row caches work. The question was, DataStax has discouraged using the row cache. What's our experience? Our experience has been great. 35% bump in throughput, latency is down, and haven't experienced any problems with it. A lot of that is that they talked about this morning, Jonathan did, that it'll bring the whole row in, and so if you have really big rows, you have an issue. And we only put our views, which are small and contained in there. So it's worked great for us. I've been surprised to hear them talk it down. But what was that?
Your model fits into Cassandra.
Yeah, yes, we are very fortunate that we fit into here well. And the underlying theme, I think, of this whole thing ought to be, you need to test your app. Right, every app is different, and you need to go try it. So here's how to configure the row cache. There's two sides to it. In Cassandra.yaml, you need to enable it. So nodes you have to tell each node how much memory to set aside for the row cache, and it does it off heap. We did 32 gigs, and so 8 times 32 gigs, we had 250 gigabytes of cache there to use. And then you have to turn it on for the individual tables. And so, as I mentioned, we did it on our tables that have small rows, not on the big ones. And then a screenshot from Ops Center when we were running. Okay, so one point to make here is you see there is about a 90% hit rate on the row cache is what we're getting. And the disk over on the top left there is the disk utilization, and it's 0, right? Because everything fit in memory. Now, the interesting thing is everything fit in memory before we turned on the row cache as well. So it was all coming out of the buffer cache, right? Linux had cached all of the files into memory. And so before we turned on the row cache, every read was hitting the key cache. It would know where it was and go straight to the right spot in the files. And those were already in memory because Linux had cached them. So everything was in memory both before and after, and yet we got a 35% increase in throughput and a big reduction in latency with the row cache. It also reduced the CPU usage slightly. So I didn't put a graphic up here, but we were about 80% CPU consumed without the row cache, and it's, what is it there? 75% or so. So just a little bit reduction in CPU usage when we turn on the row cache. Okay, so that's the row cache. That was the first big win on Cassandra tuning. The next one was when we went token aware. So this is another one where DataStax, I've had DataStax people talk it down going token aware, and yet we saw a big improvement from it. So with Cassandra, as I'm sure you know, when you go to do a read, the default load balancing strategy is round robin. So the client will pick a node and contact that node and give it its query. It will then act as a coordinator and contact the replicas of that data, gather the results, and then return them to the client. That network hop to the replicas and just the coordination of multiple nodes means you're talking to multiple nodes means that you're adding to the load of those machines and that there's network latency that you're introducing there. So cutting that out, again, a big reduction in latency from 7 millisecond reads down to 2 millisecond reads, and 50% more throughput when we went token aware. So the token aware, the client gets from the cluster which regions of the keys are in which vnodes and where those are. And then we'll direct the query to the node, one of the replica one of the replicas, which means that node has the data and can answer the question if it's consistency level 1 without consulting any other nodes. And so you get a big gain on that one. So here's how you turn that on. We're using the DataStax driver, and when you instantiate the cluster, you can pass it a load balancing strategy. If you don't, it's going to use the top one under the covers. Excuse me. It's a round robin policy. If you do, and this is what we set it to, token aware policy, and you can nest inside of that another policy, what to do with the list of replicas. So the token aware policy says, choose the list of replicas for this, for the token that's needed. And then the round robin inside of that means round robin between those three. We've had a little bit of back and forth with the other team that's using Cassandra internally around round robin versus the latency aware, where with that one, the client will keep track of the latency with each node and direct it to the one that's that has been responding the fastest. Okay, finally, the last thing, and this was an incremental gain, a 5% throughput improvement when we bumped up the concurrent reads. And this one really surprised me. I thought for sure we would need to bump these up earlier. We went from 32 to 250, to 128, 256 concurrent reads and concurrent writes that are allowed, and bumped up the native transport max threads to 256. Only an incremental gain. 16. The question was how many cores on each node? 16. Yes. Yes, you're using vNodes. Of going token aware. Of going token aware? Oh, on this one. So but you're saying because we were using vNodes, we were seeing some benefits here. And we probably wouldn't if we weren't using vNodes. Yeah, maybe. Maybe. We have not changed that number. Nope. We haven't. I was talking to the Sony guys earlier, and they've had some real issues with vNodes and lots of stuff there. Are you from Sony? You're smiling. We haven't had any problems with it. So. Okay, the comment was reduced the number of tokens on a node and saw an improvement when you did that. How much? You went from 256 to 10, and how much did it buy you? 25% gain in what? Oh, in latency, read latency. Okay, that's interesting. Okay, so this has led to a little bit of dilemma now, which we're getting adequate throughput, and we're probably not going to push a whole lot harder on this. But still a mystery for me is where is the bottleneck, and I haven't got to the bottom of this one. Nothing is saturated. The CPU isn't saturated, the network isn't saturated, and the disk is, as you saw, pretty much idle because we just all fit in memory. And yet, I can't get any more out of the cluster. So, and I thought I would share a little bit of more what I've been with that. The network side has been a bit of a mystery. So the highest ever have gotten Cassandra to use in these clusters has been 800 megabits of the network. High 1.4XLs have 10 gigabit network. They were deployed in the same, the term deployment request. That's not the right term. Placement group. There we go. Placement group. So we really can get high throughput there. I've done iPerf between all the different ones, measured. Indeed, the bandwidth is there, and yet I took a NetHogs screenshot as we're at the max, and I have never seen Cassandra achieve over a gigabit as it's there. Okay, so a little more on the network, and yeah, the network seems suspicious to me. So there's this 5-second cycle that I keep seeing, and NetStat, and I have tried, they talk about tweaking these parameters, and I've tweaked them and have not been able to measure an impact from any of those. So, the client machines seem okay at the same time. So I'll show you that here. This is let's see, the top of this is from TC, traffic control utility. And you can see right here, this means that at this moment, there's 870 packets in the queue to be processed. That's the backlog, and 2.5 megabytes. I don't know if you guys see that over here, 870 and 2 meg. And it's had to requeue 850,000 packets. So there's obviously some issues there going on with the network. And then if you look on all these sockets here, the send queue, all the send queues have a bunch of data in them. Okay, so that's one snapshot. I wrote a script here, and a couple seconds later, whoops, that was not what I wanted. A couple seconds later, the send queues are all almost empty, and the receive queues have a bunch backed up in them. All right, a couple seconds later, and it's looking fairly normal. This is kind of how you'd expect to see a healthy running network connection. And I wish I could explain it. I don't. The Amazon has their new enhanced networking. Haven't played with that yet, so maybe that will help with this type of thing. This is a high one 4XL. So there's 16 CPUs, 60 gigs of RAM. Yeah, 10 gigabit network. The application machines are all moderate network machines, and yet there's plenty of those. So there should be, and I can go put iPerf between them and the cluster and get lots of bandwidth. So I do not believe it's simple lack of bandwidth there. Okay, so that is pretty much the results of what we have found as far as the Cassandra optimizations. We have tried some other things that didn't get us anything, and so I didn't include those. And I would emphasize again that your mileage will vary. Your application is different. Those mix of queries, how much writes, the types of writes, the complexities of the writes, the types of data, the access patterns on the data, all those things vary, and so you really got to try your app and see what you find. Any questions? Does any part of the application use a blob? Yes. We're storing.
How much of data is being stored? You said terabytes, right? What portion of them are blob in the overall stack?
Almost all of our data is blob-like. We're storing it in text columns, but it is JSON. It's hex-encoded, compressed JSON that we're putting in there. Okay. Oh, there's one over here. The row size. So there's the journal and there's the views. The views are all less. We probably average 10K for the views. That's what the reads are against. And then the writes, the rows get very large because we do a column for every journal entry. So they're typically 100 up to 100,000 columns there, so they can get very large.
And were you doing multi-guest for reads or one at a time?
One at a time. We have found good success doing many parallel asynchronous reads. That's what we've done. Okay, thank you very much.